All right, let's jump right into a really interesting puzzle. We all call Earth the blue planet, right? It's covered in water. So how on earth could we be facing a global water crisis? It just doesn't seem to add up. Let's dig in.
I mean, you've seen the pictures from space, the stunning blue marble just floating there. Nearly 3/4 of the entire surface is water. So when you hear headlines about cities running out of water or major shortages, it feels wrong, counterintuitive. So what's really going on? What's the secret disconnect here?
Well, to get to the bottom of this mystery, the first thing we have to do is kind of act like accountants. We need to look at the planet's water budget. And no, it's not about money, it's about tracking every drop, where it comes from, where it goes, and most importantly, where it's all being stored.
And bam! Right away, the first huge piece of the puzzle just slaps you in the face. A truly staggering 97% of all the water on our planet is saltwater in the oceans. Now, that's great for whales and coral reefs, but for us, for drinking, for farming, for most of our industries, it's basically useless unless you go through a really expensive process to desalinate it. That leaves just this tiny 3% slice of the pie for everything else.
But hold on, it gets even more dramatic when we zoom in on that little 3% of fresh water. Because it turns out most of that water is also completely out of our reach. It's either frozen solid, locked away in massive glaciers and ice caps, or it's buried so deep underground that we can't get to it. The stuff that's actually left for us, in the lakes and rivers we can see, is just a minuscule fraction of the total.
So let's just let that sink in for a second. We live on this incredible water world, but the actual amount that is fresh, liquid, and easy for us to get to it's just shockingly small. This massive imbalance is really the foundation of the entire global water challenge. But believe it or not, that's still not the whole story.
Okay, so this is where it gets really fascinating. The second big clue to solving this whole paradox isn't about geography. It's not just about where the water is, it's about time. Specifically, it's about a concept that dictates how quickly we get our water back once it's used. And that concept is called residence time. Now, it sounds a little technical, but I promise the idea is super simple. It's just the average amount of time that a single water molecule will hang out in one place, whether that's in the atmosphere, a river, or a giant ice sheet, before it moves along in the water cycle. And just look at how extreme these differences are. It's wild. A water molecule might only float around in the atmosphere for about 9 or 10 days. In a river, maybe a few weeks, a couple of months tops. But then look at the other end of this chart. Groundwater can stay put for hundreds, even thousands of years. And water in an ice sheet? We're talking 10,000 years or even longer. Realizing this, well, it changes everything.
So this whole idea of residence time forces us to make a really critical distinction. It makes us think about water in two completely different ways. You can think of it as the difference between a paycheck that comes in every 2 weeks and a trust fund that you can only spend once.
Exactly. Water in places with a short residence time, like our rivers, is renewable. It's our paycheck. The water cycle is constantly topping it up. But water with a really long residence time is, for all practical purposes, non-renewable. It's our trust fund. If it took thousands of years for that water to build up, and we pump it all out in, say, 50 years, it's not coming back. Not in our lifetimes, not in our kids' lifetimes. It's effectively gone for good.
And when we talk about this finite, non-renewable water, we're mostly talking about two big things. First, there's what's called fossil water. This is ancient groundwater that's been trapped underground for millennia, and we're now pumping it to the surface in arid places. The other is the water that's been locked away in glaciers and ice sheets for just as long. As climate change melts them faster than they can rebuild, we're basically making a one-time withdrawal from Earth's oldest savings account.
So let's recap. We have a very small supply of accessible fresh water. Some of that supply is basically a one-time use resource. So, what's the final piece of the puzzle? You guessed it. It's us. It's how our actions are putting an almost unbearable amount of pressure on this already fragile system.
There's a quote from the material we're looking at that just nails this entire idea perfectly. It gets right to the heart of the paradox. We live in this world where water is constantly moving, constantly recycling, but the actual part of that cycle that we can reach out and use is incredibly small and vulnerable. And our actions are now pushing that limited system right to its breaking point.
We're throwing a wrench in the works in so many ways. We're pumping out that ancient fossil water way faster than it could ever be replaced. We're changing the natural flow of rivers with dams. We're even altering rainfall patterns by cutting down forests. And layered over all of that, of course, is climate change.
which is hitting fast forward on the melting of our planet's frozen water reserves. We are actively and quickly shrinking our own supply.
So there you have it. The paradox is solved. We're not running out of water on the planet. We're running out of the tiny portion that is fresh, clean, and easily available. And worse, we're dipping into ancient, non-renewable savings to get by. Which, brings us to the final and maybe the most important question. We inherited these incredible, ancient water reserves, a gift from a past Earth. What kind of inheritance are we going to leave for the people who come after us? That's something to think about.